we are going to start these lectures on nanotechnology and chemical engineering. So, in this lectures we will discuss synthesis of nanomaterials, that is physical methods. So, there are many methods that we had discussed in our previous class already. Mechanical methods by high energy ball milling methods, melt milling or melt mixing methods that we have discussed. Then we have discussed method of evaporations methods, and then today we will discuss about sputter depositions methods. So, in DC sputterings, radio frequency sputterings, magnetron sputterings. So, these methods will discuss. Also electric arc depositions method and ion beams techniques or ion implementations, that methods, and molecular beam epitaxy methods. These are the things we will discuss. So, by using this particular methods, how we can prepare different type of nano thin films that we can prepare by using sputter depositions, that we will discuss. Okay. So, in sputter depositions, here particularly this is also evaporations methods. By this way we can produce non porous compact films that we can prepare through this method, and this method widely used for thin film deposition techniques without changing the compositions of the original materials, that we can also prepare from the target materials where we can want to deposit that particular material. So, that particularly in the form of films. So, here in the right hand side you can see that is the sputter deposition techniques, that schematic diagrams of systems. So, where this is substrate green color. So, here this is the substrate and this is target materials. So, this is orange colors. So, and here's a vacuum chambers is there. Initially vacuums is we have to create in this chamber. So, after that this is step by steps we are going to discuss. Here first control the inert gas, that inert gas may be argons that we can introduce into these chambers. First we have to vacuums and then we have to use the inert gas, that is argons, we have to introduce into these chambers. After that a negative voltage that would be applied to the targets, that this is the targets material. So, here we have to develop negative voltage as if it can generate some plasma. Okay. So, high speed gas ions or argon, that is the plasma, that would be ejected from the target, and then these ejected atoms that would be added to the substrates that would form say thin films. Okay. So, this argon ion that would be interact with this target materials, and then the plasma interactions, that materials will be falls and put over the substrates, and that is in the forms of nanofilms. Okay. And this since there is no, initially it was vacuums and then inert gas was used. So, therefore, the films that would be deposited, it is highly, means extremely high quality, means impurities will be very low or less in this particular sputter deposition methods. So, in these methods we can control the film thickness and quality, means if we able to maintain a high pure gas, high pure materials. So, then high quality, the quality of that materials without any contaminations we can prepare. Also film thickness also we can prepare. So, depending, means highly, means thin films, film thickness different type of, maybe means 2D type of material. So, here the film thickness small or large, that we can control by controlling the concentrations. Okay. Suitable for high melting point metals and alloys, oxides or nitrides. These particular methods to deposit the thin films, it is very suitable. Okay. So, where the metals or metal oxide that are being high melting points, so alloys also oxide, so that we can use this part deposition methods to deposit or create a particular films. So, its particularly use or applications, means this part are depositions methods. Here semiconductors, wiring and barrier film formations it is used, and also transparent conductive films that can be produced through this method, that is very useful for smart devices. Also decorative coating, automotive reflector processing, they are also these sputter depositions can be applicable. So, these sputter deposition techniques we can categorize three different types, means direct current or DC sputterings, we can say radio frequency sputterings. So, in and also Magnetron sputterings. So, that is third type. So, here or maybe combinations also we can use. So, direct current sputterings, here DC current we have to use, and RF sputtering, radio frequency, that we can use for sputtering process, and magnetron sputtering, there magnetic fields that can use, or either with the DC current or RF magnetic field also we can apply to prepare that materials, that film. Okay. So, first we will discuss about direct current or DC sputtering. So, in this particular method, so you can see in which sputter target is held at high negative voltage. Okay, the targets that would be high negative voltage, and substrate may be positives or grounds or floating potentials, and the substrate may be heated or cooled depending upon our applications or the way we are going to prepare, either it is heated or cooled. And once required pressure is attained, then vacuum systems and argon gas will be introduced, and that pressures may be less than 10 pascals. So, inert gas, I said at the beginning also, argons that we can use, that would form a plasma, argon plus, that would be a forms that would interact or with the targets, and then that visible glow will be observed, means when this argon plus, that ions that would be forms or plasma will forms, and that would interact with this, and a positive glow discharge that will be develops in this particular place, and then over the substrates, that materials that would be deposited over here, and that way we can and get a particular films of nanomaterials. Okay, so here in for this particular process, DC current I said that would be used, that would be generates a glow of discharge then between cathode and anodes, and this is negative and this is positive, or it may be odd things. So, when some argon gas is there, so that would be ionized or plasma formations is there, the positive ionic charge of argon plus, that is called plasma. Okay. So, that would interact with the these electrodes, and then it would forms or deposit some atoms that would be in the form of thin films over the substrate. Here it would be deposited. So, and if the substrate part or this component is cold surface, so there's we can get that films. Okay, thin films we can get. Okay. So, here's plasma atoms, so that is ejected atoms that is deposited on that particular surface. Okay. So, next is the radio frequency. In earlier one, that was the DC sputtering. So, DC voltage that was used in between two electrodes, and then plasma formations is there. So, now we have to use radio frequencies, that radio frequency that helps to for sputtering process. Here high quality and uniform themes we can generate by using radio frequency. So, here if the target is insulating, suppose the target materials that may be conducting or maybe insulating. So, if the target is insulating, it is difficult to use DC sputterings. Okay. So, DC sputtering methods when we are going to use, then target substrate may not be insulating materials. If it is insulating, then we cannot use the DC sputtering process, then you have to choose for radio frequency sputtering process to generate plasma generations. Okay. So, that particularly useful, and this particular radio frequency means both it can be used for conductive and insulating, whatever the both the either type of materials we can use RF sputtering process, and but DC sputterings only if means conducting materials is there, so then we can use that. Okay. So, this for conductive materials only we can use, or radio frequency both conductive or insulating, whatever the materials, either way we can use both conductive and insulating materials you can use, and exceptionally high voltage that you have to use for this process to sustain a discharge between two electrodes. Okay. And the alternative RF power, radio frequency power, prevent charge buildups on insulating targets. Actually, when you are using radio frequency powers, that build up a charge on that insulating materials, after that ensuring continuous ion bombardments and efficient material ejections from that source. Okay. So, in this I said in radio frequency conducting or insulating both we can use. So, if the material is let us say insulating, then radio frequency that charge will be built up on that particular materials, and then evaporations will be there and plasma formations is there. So, that would be deposited over the surface Okay, so in this process we can get high quality or uniform thin films, and applications, many applications are there. So particularly electronic or microelectronic applications, optical coating or depositions of dielectrics or ceramic film formations. So here's radio frequency as sputtering process or setups or schematic diagram is showing. So this is vacuum chambers, this is substrate anode, and this is cathodes, and here the plasma process formations is there. Some particular gas or argons we can use. This is the, here you can see the radio frequency. Here's nickel oxides, yellow means nickel, what is the circles, that is nickel oxide substrate that is here at this particular cathode. So here's plasma that would be heated up or targets, here it would interact and then it would be evaporated and deposited in that anode substrate. So here it would be deposited. So next is the Magnetron sputtering. So in this process we can produce thin films. So in this radio frequency or DC sputterings, rates can further be increased by using magnetic fields. So either radio frequency or DC sputtering, both we can use for thin film formations. Both these are evaporation methods. So apart from these two, to enhance its efficiency, we can use some magnetic fields. So here is the cathode at the bottom. So here you can see. So here we can put some magnets that would enhance actually that magnetic fields. So both electric and magnetic fields act on the charged particles and force it to given by a Lorentz forces. And say widely used thin film methods, semiconductor optics and microelectronics, here we can use these Magnetron sputterings or thin film formations. Here means with this additional magnetic fields we have to use to enhance the methods or productions. Okay, so here's common sputtering gases that we use. These are the inert gases we use, argon, krypton, xenon. So sputtering gases. Apart from that, some reactive sputtering gases also are used, that may be oxygens and nitrogen, depending upon our source materials, which ones we want to prepare. Depending upon that also reactive sputtering gases also we can use. Okay, so this is the targets and this is the thin film formations. Okay, so power source determines means here I said with DC magnetic fields we can use, it is called DC magnetron sputterings. In this case conductive targets, for conductive targets we can use, or RF magnetron sputterings for both conductives and non-conductive materials we can, or insulating materials we can use RF magnetron sputterings. Okay, so by if we use let us say different type of metals, let us say alumina, titanium, tungstens, and with that some gases we can use, means reacting gases, that may be H2S, oxygen, nitrogen, for ammonia. So then what would give, means individual metals to metal oxide, metal to metal nitrates, metal to metal carbides, that we can generate depending upon our source and final product of interest for this particular sputtering method. So we can prepare that. Next is the electric arc depositions methods. So in this particular methods we can prepare fullerenes and carbon nanotubes. So fullerenes I said C60, C70, that is 0 D, and nanomaterials. So in electric arc depositions, this is another method. So through these methods we can prepare, these are the components. So here's one vacuum chambers is also there. So water cooled vacuum chambers, this is water cooled vacuum chambers, or this one. So here two electrodes are there, electrodes 1 and electrode 2 in this vacuum chamber. So here's in this electrodes materials that we have to use, both are graphites we can use as source materials, electrodes, inert gas that we have to use between two electrodes. There is a gap just 1 mm we can use, and in between these two gap is 1 millimeters, very small gap, and we can develop high current 50 to 100 angstrom ampere, and low voltage we can apply for this particular process. And this is inert gas chambers I said, and it is vacuum chambers, and cold outer sides, this is the cold water cooled jackets would be there, and then this is one electrode, this is another electrode, two graphite electrodes we have to place there, and then a arc will be developed, and then anode material, this is anode materials, these materials will be evaporates. Okay, so anode will be evaporate out gradually with time being, the anode materials size will reduce, that will decrease. So then adjustments of the electrode gaps with breaking, without breaking the vacuums, one of the electrode bonds and gaps increases. So here's the systems will be like that, this electrode gradually, this is graphite electrode, gradually it will be decay by evaporation, so gaps will increase, and then again there is some adjustment process. So without means breaking the vacuums, that would move this forward directions, maintain that same gap, and by that way we can continue this process and we can get different type of nanomaterial, that fluorines, carbon nanotubes. Okay, so inside of these vacuums, that is very important. Okay, so when we are going to prepare, means either fluorines or carbon nanotubes, which one we are going to prepare in this particular method. So here if we want to get fluorines, so then vacuum pressures inside of that particular vacuum chambers, you have to keep very low vacuum pressures that you have to maintain to get fluorines. Okay, so fluorines are obtained in these vacuum chambers, that would be collected in the form of soot. Okay, inner wall of that vacuum chambers, this is the inner wall of the vacuum chambers. In this particular walls, some soot will be deposited, that we can collect from that walls in the vacuum chambers, and then we can purify to get fluorines. Okay, and if you want to prepare carbon nanotubes or CNT, for that we have to develop, or we have to create high pressures in that chambers, and then carbon nanotubes that will be forms. Here's this cathode is there, so here's in the central portions of the cathodes, there's these carbon nanotubes will be deposited, and we can collect that from that cathode. Okay, and no carbon nanotubes that would be deposited at the surface, this surface no CNT will be deposited, only fluorines will be deposited at this surface of the walls, we can get fluorines, and carbon nanotubes will be deposited at that cathode materials, cathode surface. Okay, so here you can see mobile anodes is there, this is the anode that gradually will be evaporated or decay, and due to this electric arc deposition process, is size of these materials will be gradually decreased, and then through movements it maintains the same distance between two electrodes, and by this way you can get that desired, either it is fluorines or carbon nanotubes. So in this process I said direct current or DC we can use, high current you have to use, low voltage you have to use. So in this particular process, high temperature, extremely high temperature 3500 degrees centigrade plasma temperature will be developed within this small space in between two electrodes. Okay, so next is the ion beam techniques or ion beam implementations, IBT techniques. So in this process also various types of metals we can deposit in the form of films, depending upon our targets or depending upon our interest of the materials. So here some ion source is there and some target is there also. This is the substrate, here we can deposit. So here this ion source is there, this ion beam interact with the gaseous molecules. Here you can see gaseous molecules. So with that this ion source will interact and generate sputtered atoms, that will be deposited over the surface in the form of thin films. These blue colors you can say this is the sputter atoms that will be deposited in the form of thin films. So in this ion beam techniques, so we can generate a particular type of thin films by considering particular materials, or maybe two different, three different also materials we can produce. Okay, so here's ion guns that is used oxygens or carbons to produce metal ions that would be accelerated to high or low energy towards the substrates and heated to the few hundred degrees centigrade, 3500 degrees centigrade I said. It is possible through this process a single element nanoparticles that we can produce through this particular process, and or compounds we can produce alloy more than one elements. By using one elements or more than one elements, that would be we can say alloys that we can also produce, and post annealing methods or that process we can use to improve the crystallinity of the materials. Okay. So, I said one or two materials we can use, at the same time some other doping materials or foreign materials also we can use to dope that particular metals with that some percentage other contaminations. If it is helpful for a particular process, that also we can choose for this particular process to develop that particular nanoparticles. Okay. So, next is the molecular beam epitaxy methods. Okay. So, this is another methods, physical method. So, by that way also we can develop for growth of semiconductors, crystalline growth, so we can develop. Here several atomics, molecular beams guns or beams that can be used to deposit that atoms over a particular surface where you want to deposit. Okay. Here through these methods we can develop quantum dots, quantum wells or quantum wires. This type of materials we can prepare using molecular beams epitaxy method. So, here is a schematic diagram of epitaxy, molecular epitaxy means methods or schematic diagram is showing here. This is in this particular systems there are two things here. You can see this is the cryo panels is there that would maintains low temperatures, and here is the substrates. So, you can see okay, substrate we can manipulate by using some holder is there, so we can go up and down, and means that positions of the substrate we can change as per our required, and temperature we can maintain by cryo panels. And then in the left hand side there is effusion cell is there. The effusion cells we are showing here. In effusion cells, this is one particular metals, this is another efficiency 2, 3, 4 many types we can use. And here in effusion cells there is an closed barrier is there, with that there is some pore or orifice is there, through that small pores orifice is there, through that whatever the materials we are going to diffuse or pass through this particular chamber. So, that cell is important. So, here it would be target like this, means if it is let us say nickel is present, so nickel would be deposited over the surface. If it is another metals, that when it is required we can heat it up and then pass through this orifice and would be deposited over there. Similarly, this and that also. So, this type of chamber is there. So, here you can see metal 1, metals 2, metals 3 we can means put in this particular effusion cells. So, it would be heated up, that would be vaporized, and that would be passed through this orifice, and it would be deposited over this target points or the substrates where we want to deposit. Okay. So, here you can see right hand side. So, here blue, that is reds or yellow, three different type of metals we can consider in the effusion cells. So, here Sputter switched switch beams on off is there, means here depending upon when it is recurs, on that times that would be on or off, and that beams will be falls over this particular surface, and that elements will be deposited, or layer of atoms that would be built up over the surface. As per our preparations of the materials we can do this. Okay. So, in effusion cells already have discussed. Okay. So, here's effusion cells key components is provide excellent flux stability, uniformity and material purity, and collections of gas molecules moving in the same directions through this effusion cells. I said these directions it would move toward the substrate, and ovens contains materials to make the, here's oven is also there I said. So, here's means that would be heated up that materials to make into vapors, first melt and then vapors, then substrates will be here it would be that particular desired metals that would be deposited over there. So, here you can see the evaporated atoms don't interact with each others in that vacuum chamber, so where we are using. So, until they reach to the wafers, these metals atoms that would be falls and deposited particular surface, this is also deposited particular surface. Okay. So, So, high degree of purity is achievable through this process, molecular beam epitaxy, and node sense cells or effusion cells we can say, that is employed to obtain molecular beams of the constituent elements, the materials or metals, or we need to deposit a particular surface that you have to take in that particular node sense cell or diffusion cell or effusion cells, and that would be heated up with the furnace, and then that would move to that particular desert towards that substrate. Okay. So, rate of deposition is kept very low in this particular process, as if substrate temperature also is very high, and layer by layer deposition or growth of that particular films is possible. Also high purity thin films that is possible to form through this process. Okay. So, there are many methods that we have discussed. So, thank you so much. Okay, thank you.